Hey guys, it's time for the second part of Power Standard 3, Learning Target 2, Resistance, Current, and Voltage. You just finished the easiest part on conductors and insulators. Now you're ready for the hardest part of the whole entire thing. So we're going to take these three words, resistance, current, and voltage, and kind of explain what they mean. But first, I want to make sure you have a definition for circuit. So circuit, C-I-R-C-U-I-T, circuit, is a complete path through which charges flow. So we can make a simple circuit here that you have, I only have one wire. You have a wire, a ball, battery, and I can actually connect it here, and I can make my light bulb light up just a teeny tiny bit. So this is a circuit. The charges are flowing through this whole entire thing. I can make a short circuit by not having a light bulb. And now my charges are flowing. The electrons is actually what's flowing in this wire. When I unconnect it, the electrons are still in the wire. They just stayed still. They'll stay still until they're connected, both pieces, to a closed circuit. So this is called a closed circuit because everything's connected, which means the electrons will start flowing through the wires. I have this racetrack down here because it's kind of similar. The racetrack needs to be a complete circuit in order for the cars to move. If you take one of these pieces off down here, then it's an open circuit. And then the cars won't move, the electrons won't flow. So now I want to get back to like resistance, current, and voltage. Those three words are so confusing. I bet you if you talk to your parents, they'll be confused of which one is which, unless they have some sort of job in like engineering or electricity work. So here's the first one, current. See how it's different than circuit? Current is very similar to the river's current. In the river, the current is how fast the water's going down the river. So in a circuit, current is how fast the electrons flow through a material, or here in the definition of electric charges. But we know that really is electrons. So it's the continuous flow of electric charges through a material. So I have this random conveyor belt here. Those tomatoes represent electrons. And right now he's inspecting the tomatoes through the conveyor belt. And it has a nice steady flow. But I could increase the current. If I increase the current, look at those tomatoes are going so fast. How is he going to inspect each one to make sure they're all high quality? I just made the electrons flow, or the tomatoes flow faster. So you can do that with your circuit. We can have one battery, we can put a couple batteries here, and that would change the way our electrons flow. Of course, the more batteries you have, the higher they're going to flow. So here's an example. It made me think of this plunger thing that we get, not plunger thing, but like this like syringe that we get with my kids' medicines. So I can make water flow slowly. That's like a current there, that me pushing out the water. Or I can make the water go rather quickly. I'm doing something different. I'm pushing it differently between the slow and the fast. That push also has a term. So the flow itself, the flow of the water is current. But what is this plunger thing? This is what I'm doing differently. That represents another piece of the puzzle here. So that's called voltage. You probably heard of voltage before. Voltage, it's a tricky definition, is the difference in electrical energy in a circuit. The unit here is volt. So if you look at your batteries, small underneath the D, can you see? It says 1.5 V. So this battery is 1.5 volts. That is the push that the battery is providing to get those electrons through. They're actually like pushing them along. Voltage causes the current. I want you to write that down and like underline it, put little arrows next to it. Voltage causes the current. And the voltage source is something that creates voltage, is the source of voltage. So in class we've been using batteries. We could also be using a generator. We could also be using outlets, but we don't want to hurt you. So we use batteries. The outlets is too much power. Sorry guys. So back to my example with the syringe. If I fill up my syringe again, here's the current. This is the voltage. The plunger itself is pushing that and causing the current. So depending on how fast I push is how fast the current goes. The more voltage, the more current. So that this illustration showing the voltage is like the little piston here pushing the liquid out. Just like the batteries of voltage pushing those electrons around. The more batteries, the greater push you have, which means more current. More voltage, more current. They're related. Heart. Okay, you got it? You got 2 there. Voltage makes the current flow. Current is how fast those electron boogers are going. But what's going to make them stop? Dun dun. Okay, that's called resistance. If I probably bet you've experienced resistance before with something you wanted. Maybe you wanted to go to Skateport or to the mall with just your friends, and your parents offered resistance. They didn't want you to go there by yourself. Maybe you're too young, or maybe they don't trust the other people. So they resisted that idea. Resistance is like opposing something. Opposing means stopping. So for electricity, resistance is the measure of how strongly a material opposes the flow of electric current. I have a light bulb there in the corner because that provides resistance. The light bulbs shine because in the middle of the light bulb there's an itty bitty wire. That wire is so small the electrons can't still flow through them because the electrons are smaller, but it provides so much resistance that that wire burns and glows. That's how light bulbs work. It's called a filament. Here, wires can also create resistance. What if I have a nice open wire, maybe like a hose that's big and open? Then the water or the electrons can flow. If there's a wire, electrons can flow easier. But what if I put a kink in it? The water can't flow so well. If I have a very skinny wire, the skinnier the wire, the harder it is for those electrons to flow. It just makes kind of logical sense. So resistance is opposing the flow of electric charges. Every time we add a light bulb to a circuit, we add resistance. There's 4 factors that affect resistance. One factor is how long the wire is. The longer the wire, the harder those electrons have to work. The second one I have down is thickness. The skinnier wires are harder for the electrons to flow. That makes kind of sense. Think of a skinny pipe versus a wide pipe. The wider the pipe, the easier it is for the water to flow. Same thing with wires. I have some skinny wires and I have some fatter wires. The fatter wires, the electricity flows easier, so the light bulbs shine brighter. The temperature also makes a difference. We don't test this in class, but the temperature does make a difference. The hotter it is, the easier it is for the electrons to flow, because the electrons are already moving. Remember in 6th grade we talked about heat? When things are hot, the electrons are excited, so they're moving already, so it's easier to flow. Finally, the material of the wire. Some materials are better conductors than others. We learned that last time. But like gold. Gold is a great wire because it has very low resistance. They use that to build airplanes and rockets because it's such a great material. Copper is also a great material. It offers very little resistance, a little bit more than gold, but it's a material we often use in wires also. So write these 4 down. You might want to draw this illustration, like wide pipes, the wires, it's easier to flow than small wire, like narrow. Short has less resistance than long. I mean, it kind of makes logical sense if you think about it. Here's some relationships. I want you to think about this. As the voltage increases, current, what do you think? Increases or decreases? As resistance increases, current, what do you think? Increases or decreases? As voltage decreases, the current. Finally, as resistance decreases, current. I want you to understand how these things work. So, let's check your answers. As voltage increases, which means you add like more batteries, then the current increases. 2 batteries work better than 1 battery. As the resistance increases, resistance would be like adding more light bulbs. When you add more light bulbs, that current goes down because you're making those electrons go through multiple bulbs. That's hard. Okay, as you decrease voltage, you maybe go from 2 batteries to 1. The current's going to go down. You gave it less push. Remember, voltage is that push. So you gave it less push. That's harder. As resistance decreases, oh, that's good. Maybe you had 3 light bulbs, you went down to 2. So as you lose resistance, the current does go up. Okay, you have a couple activities that'll help you along with this power standard. But if you don't understand, please stop and ask. We are here to serve you. Okay, guys? Take your time with this one. This one's the trickiest one. And we want you to be successful. Hope you guys have a great day. Talk to you later, Gators.